Okay, we're going to now take a look at another aspect of rational functions. In the last video we talked about vertical asymptotes, and in this video we're going to talk about horizontal asymptotes, or what we sometimes refer to as the end behavior. Now, end behavior for polynomial functions, if you remember, had one of four different shapes, if you will. Remember that the polynomial functions can rise to the right and to the left, or they can fall to the right and to the left, or we can have a situation where we're rising to the right and falling to the left, like in the function x cubed, or we can be, again, falling to the right and rising to the left. So these are the four different end behaviors, if you remember, with polynomial functions, and we use the leading coefficient test to determine those behaviors. And some rational functions have these same four behaviors, but others will have a different behavior, and we want to look at this now. In fact, I want to look at two functions, one real simple and one a little more complicated looking. This simple function, 1 over x, is actually one of our basic functions, if you remember from the beginning when we first introduced the 8 basic functions. And what I'm interested in now, again, is the end behavior. So what do I mean by that? I mean when the value of x gets arbitrarily large. So that can be getting large and positive. So for instance, x can become, we can plug in values like 100 or 1,000 or 1,000,000 or 1,000,000,000 and so on. We want to get bigger and bigger and bigger, and we want to see what's happened to the value of the function. Or we can plug in values that are becoming larger but more negative. So in other words, negative 100, negative 1,000, negative 1,000,000, and so on. Well, it's pretty easy if you think about this function. You're dividing 1 by whatever your input is, x. And so as x gets larger and larger, let's say from a positive value, what's happening? 1 divided by a positive number is always positive, but since you're dividing 1 by a larger and larger value, then the overall output is getting smaller and smaller. So for instance, if we plug in 100, we get 1/100th or 0.01. If I plug in 1,000th, I get 1,000th or 0.001, and so on. Those values are getting smaller and smaller, but what we observe is they're getting closer and closer to 0. And here's the graph of the function 1 over x, and you can see that as we input bigger and bigger values, the output's getting closer and closer to the x-axis to 0. By the time we plug in 10, again, we get 1/10. But imagine if I went way, way out here to 100 and plugged in, what would the output be? Well, it would be 100th, 0.01. And it would almost, if we're looking at the graph, it almost look like the graph actually touches the x-axis, but in fact it never does. If we plug in values that are negative and large in absolute value, like negative 10, negative 1,000, and so on, the value of the function 1 over x is always negative, but again, getting closer and closer to 0, getting closer and closer to the x-axis. And so we talk about this behavior this way. We say as x goes to infinity, f of x is equal to 1 over x is approaching 0. And as x approaches negative infinity, right, as the value of x goes to this end, looking at the end behavior this way, then the function is going to 0. And so the function looks like neither one of these four types. If we zoom way out, it looks just like essentially the x-axis, a line, almost looks like a line coinciding with the x-axis. Okay. Let's take a look at this function, and I want to look at it numerically real quick. I've got it in my calculator already. I've entered in this function here into my calculator, and I want to take a look at it numerically by going to the table like we did with the vertical asymptotes, but this time I'm going to want to know about the end behavior. So I want to plug in bigger and bigger values of x with first two positive values. I want to see what happens to the value of this function as that happens. So I can plug in 10, and you see the output is about 2.33. If I plug in 100, it's about 2.03. If I plug in 1,000, it's about 2.003. And we'll go ahead and plug in 10,000. Okay, so what would you say is happening? Does to the value of the function as x gets larger and larger. And you can, this is the rounded value. You can see the truncated value down here at the bottom. But you can sort of see we're kind of, as we move down the list, we're getting more and more zeros here. And it seems like we're getting closer and closer to maybe what? Something like 2, right? Getting closer and closer to 2. We're just a little bit more than 2 each time. And in fact, if you do 100,000, it's exactly 2. Well, not right, not exactly 2. If you go here and highlight, it's actually this, right? But rounded off, it's 2, right? But again, you see how it's getting closer and closer to 2. And this is what's happening. As x gets larger and larger, we're getting closer and closer to 2. We're always a little bit more than 2. We're never exactly equal to 2, but we're getting closer and closer to 2. Okay. In the other direction, if I want to look at what's happening as I approach negative infinity, we say, I plug in bigger and bigger values, an absolute value, but they are negative. And you can see as I do this, what do we appear to be approaching? Or do we appear to be approaching anything? Okay. You might say, hey, looks like 2 again. Right? If I look at the actual value here, by the time I plug in, and that's 1e to the 5th, 1 times 10 to the 5th means a 1 with 5 zeros after it, right? So it's negative 100,000. And the output is, this, of course, rounds off to about 2, but it's still less than 2. But again, we're getting closer and closer to 2. And so let's take a look now at the graph of this function here. We can see it right down here, and as we observed, now there's a couple of vertical asymptotes again. Now we're not talking about vertical asymptotes, but notice as x goes to infinity in this case, this function g of x is getting, we said, closer and closer to 2, but was always a little bit more than 2, right? And this dashed line right here is the line y equal 2. Horizontal lines are always y equal, constant y equal 2. And so we're getting closer and closer to 2, and that's the way we write. As x goes to infinity, g of x, the function, is approaching 2. And notice as x goes to negative infinity, we were also approaching a 2, and you can see what happens. It's always, we cross over the horizontal axis actually right here. But as we continue on, as x gets more and more negative, negative 10 and so on, we're coming closer and closer to that dashed line, y equal 2. But we're always below it over here, as we saw. But we still say we're approaching 2. Okay. Now, the line y equal b, in this case y equal 2, is a horizontal asymptote of the function y equal f of x if y approaches b as x goes to infinity or negative infinity. And that's what's happening. We're approaching 2, and so the horizontal asymptote is what we call this dashed line. So it's like a vertical asymptote in some respects. One thing that's a little different you'll notice is we can't touch or cross the vertical asymptotes with these types of functions we're dealing with, but you indeed can touch and cross the horizontal asymptote many times, potentially, with these type of functions. And I'll just observe, notice right here, we do intersect the horizontal asymptote right here at a value, some x value close to negative 1. The output is close to 2. Okay. Up here for this function, then we would say the horizontal asymptote for the function f of x equals 1 over x is the x-axis, which is the equation y equals 0. Notice the x-axis is y equals 0. Right? It's a horizontal line that coincides with the x-axis. That's the horizontal asymptote. Okay. Well, let's look and see, how do we find horizontal asymptotes? We can certainly sort of analyze them as we did these two functions, but let's take a look at how to find horizontal asymptotes a little more algebraically, if you will. So here's all the details. You don't get caught up in worry about all the notation. Looks a little crazy, but what we have here again is a rational function. I'm just emphasizing that there's a polynomial p divided by a polynomial q. If you remember polynomials, we talked about the degree of the polynomial, and what I've done is just written an arbitrary polynomial in descending order. The highest degree term is first, which has a degree of n, so we're saying this is degree n, whatever it is. And then the q, the denominator, it's a polynomial of degree m. Okay? And then the coefficient of the top polynomial is a subscript n. And the coefficient for the leading term for q is b subscript m. Okay? Now, here's the way we can classify horizontal asymptotes. One of three possibilities. If n is less than m, what is n and what is m again? N is the degree of the numerator up top. M is the degree of the denominator down below. So if the degree of the top is less than the degree of the bottom, then y equals 0 is a horizontal asymptote. And that's exactly what happened, if you recall, with the example we saw with the function 1 over x. Because the degree of the top is 0, there's no x term at all. The degree of the bottom is 1, so the degree of the bottom is more than the top, or the degree of the top is less than the bottom, and so that tells me that y equals 0 is a horizontal asymptote, as we said right here. Okay. Now, if the degrees of top and bottom are the same, if they're equal, then we have a horizontal asymptote, and the way we find it is actually to simply take the leading coefficient of the numerator and divide it by the leading term coefficient of the denominator. We say it's the ratio of the leading term coefficients. So y equal that is the horizontal asymptote. Now take a look at this second example. Notice the degree of the top for the function g was 2, the degree of the bottom was 2, so they're the same degree. And so what's the horizontal asymptote going to be? It's going to be the leading term coefficient of the top, which is 8, divided by the leading term coefficient of the bottom, which is 4. 8 divided by 4, what's that? That gives us the y equal 2. Okay. Now, there's one more situation, and that is the degree of the numerator is greater than the degree of the denominator, and in that case, we have no horizontal asymptote. And in that case, what would the end behavior be? We wouldn't have a horizontal asymptote. In that case, the end behavior of the polynomial is going to go back to one of these types, basically. One of these types. The book does talk about, if you read in the book, about something called a slant asymptote. And a slant asymptote happens when the degree of the top is exactly 1 more than the degree of the bottom. I'm not going to really go into that for you guys, but that's essentially one of the specific, special cases of this case number 3. So let's take a look at 3 examples. So find the horizontal asymptote for the following rational functions, if any. So again, I look at this, and we're going to look at the degrees, right? Based on this analysis up here, what's the degree of the top here? Degree of the top is 1, right? Degree of the top is 1. What's the degree of the bottom? The bottom polynomial is degree 2, right? Highest degree term is x squared. So look at the degree of the top is less than the degree of the denominator. So what case are we in here? We're in case number 1. Therefore, y equals 0 is the horizontal asymptote. Now, finding the horizontal asymptote, you've got to either A, remember these 3 categories. So you have to, memorize these 3 cases and remember what happens in each of these 3 cases. But there is another way to do it without memorizing, really, to help remind you, and that is, if you think about, for large values of x, let's look at the numerator. For large values of x, as I plug in bigger and bigger values of x, and I'm thinking again, really big, 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000. 3 times 1,000,000,000,000 is a large number. If I take away 7 from 3 times 1,000,000,000,000 or 3,000,000,000,000, subtracting 7 is almost insignificant. Think about if you had $3 trillion and you handed out $7. You wouldn't even miss it. It'd be, just a few, would be insignificant. And so what we're saying is that for large values of x, this term here, the largest degree term for the polynomial, dominates. And so for large values of x, as x goes to infinity, then y is going to be approximately up top 3x, and down below, the term that's going to dominate is going to be the largest degree term, which is x squared. If you think about x versus x squared, think about a million. Well, a million, that's a lot. A million, right? A 1 with 6 zeros after it. But a million squared is a 1 with 12 zeros after it. That's a heck of a lot bigger than just a million. So this squared term is much larger, dominates. And so for large values of x, the function y is about the same as this. If I were to calculate, this expression for x being a billion or a trillion, and the original one for a billion or trillion, they would be essentially the same. The difference in the y values would be almost insignificant. But now when I do this, how do I simplify this? Notice this x can cancel with one of the x squares, and I get 3 divided by x. Well, what's happening to 3 divided by x is x gets bigger and bigger, as we say, as x goes to infinity. Well, x is just going to get bigger and bigger. 3 divided by a larger and larger number is getting closer and closer to 0. Right? That ratio is getting smaller and smaller, and we say it goes to 0. And that tells me what to put for my horizontal asymptote. Keep in mind the horizontal asymptote is not 0. It's y equals 0. You have to give the equation y equal. Remember, horizontal asymptotes, y equal a number. Vertical asymptotes were x equal a number. All right, let's take a look at this one. We'll do it both ways real quick. The degree of the top and bottom are the same. The degree of the numerator and denominator is equal to 2. And so they're the same. So what happens if the degrees are the same? Horizontal asymptote is the ratio of the leading term coefficients. So what are the leading term coefficients here? Up top I have what? -3. Right? Because x, -3x squared, right? It's minus 3x squared or plus a -3x squared. That's the highest degree term. Highest degree term here, so 4 is the leading term coefficient there. And so I get y equals negative divided by positive is -3/4. That is the horizontal asymptote. And again, I could have gotten that by simply noting that, right, as x gets closer and closer, gets larger and larger rather, then f of x is approximately the highest degree term up here, -3x squared. Highest degree term down here, 4x squared, right? And what does that simplify down to? X squared divided by x squared is 1. That's just exactly equal to -3/4. And that's how we get that. Remember again, the horizontal asymptote is y equal -3/4, not just -3/4. Last case, the degree of the top is what? 4. The degree of the bottom, 3. Now the degree of the top is larger than the bottom. What's that tell us from our list? If n, the degree of the top, is greater than m, the degree of the bottom, there's no horizontal asymptote. So there's no horizontal asymptote. Turns out in this case there's something called a slant asymptote, as I've mentioned, but we're not going to worry about that. Again, I can analyze this. If I think about as x goes to infinity, then s of x is about equal to the highest degree term up top over the highest degree term in the bottom. And I can simplify this. Notice I've got 4 x's up here, 3 down here. I can cancel 3 x's with 3 x's, leaving me 1 x up top. And think about x divided by 2. If x is getting bigger and bigger, going to infinity, right? If I'm letting x be 1,000, a million, a billion, a trillion, and divide by 2, this ratio is half as much as my number, but it's still getting bigger and bigger, right? It's approaching, we say, infinity. And in fact, the end behavior for this rational function will be that it will increase to the right. Increase to the right. And in fact, we can tell already too, we can do the analysis that it's going to decrease to the left because, in that case, x would be a negative number, but it would still be going to, unbounded, it would be going to minus infinity. But that's the behavior of this function. Something like that. The important thing is no horizontal asymptote. Okay? So I hope that helps you understand how to find the horizontal asymptote. Now that we know how to find the vertical asymptotes, horizontal asymptotes, the rational functions, we're now ready to put it all together. And in the next video, that's what we'll do. We'll sketch a couple of examples of rational functions.